So Professor Campbell, I'd like to just introduce here with a few words. He has a PhD from Yale University and did a postdoc at the University of Chicago, which, if you're into trivia, was a founding member of the Big Ten Conference. Not many people know that. He's been at UM since 1989 and served as chair of the physics department and as associate dean for natural sciences. He's worked on projects at the Brookhaven National Laboratory, the CERN Super Collider, Fermilab, and most relevant today at the JPARC Proton Accelerator in Tokai, Ibaraki, Ken. And today he'll be describing the high energy experiment that he's been working on at JPARC and its significant accomplishments in the field. So let's please welcome Dr. Campbell, and I'll be back for the Q&A at the end.
Okay. Thank you for that introduction, and thank you for the invitation to be here. So I do want to talk about my experience in working in Japan and also give some background to high energy physics, what high energy physics is, what we are trying to do, and also explain a little bit about why Japan is one of the leaders in this particular area of research. My background, of course, is in physics, and I've tried to make this not too technical. If you have any questions as we're going along, or if you have any comments as we're going along, please feel free to shout them out or interrupt me. I'm happy to explain things in more detail if it's not clear what I'm talking about. So let's get started. So this is from the Department of Energy's Office of Science statement about what the goals of high energy physics is. And in short, it's to understand matter and interactions between matter and where matter moves, space and time itself. So it's a somewhat lofty goal, but it's just, let's understand what's going on with stuff, how stuff interacts, and how stuff moves. So in this process of trying to understand things on the smallest time and distance scale, fundamental particles, we have found a deep connection to understanding things on the largest possible scale, and that is the universe as a whole. Understanding how the universe, how it works, how it comes into being, depends on understanding things at a microscopic scale as well. And in particular, there's a thing we'll be coming back to. This baryon to photon ratio, I'll come back to that in a little while. What we do know about the universe is the stuff that we are made of, and this room is made of, and the sun and the planets is made of, makes a tiny fraction of the total universe. There's a much larger fraction, which is, we call it cold dark matter, and the larger fraction still we call dark energy. And the totality of here is known actually very precisely through a number of experiments. Dark matter, we know there's been lots of experiments on it. We know that it is particles, not just a bunch of dark rocks that we can't find. And this dark energy, well, really all that we know about it is its name. We don't really know much more. But this is the total, and what we want to do is explore this in more detail. We have a model of particle physics that works extraordinarily well in being able to make predictions. It's an effective theory that is being upheld by numerous laboratory measurements, and there's no known experimental disagreements with this model of particle physics. But there are things that are outside that model. It doesn't include gravity, and it doesn't include the dark matter and dark energy I just mentioned. And there's also questions that it doesn't answer, like why are there 3 generations of quarks and leptons? What's going on with these neutrinos? And what's the origin of electroweak symmetry breaking? In order to answer those questions, we mount an experimental program. So we design experiments that are focused on answering these kinds of questions. To answer questions about what's going on at very high energy, we go to the highest energies that we know how to make. To make progress on understanding dark matter and dark energy, we need to make detailed observations of galaxies and stars in the universe. And to understand neutrino properties and to look for rare processes, we need accelerators that have very high intensity. I want to distinguish high energy from high intensity. High energy is like being in a jet plane by yourself going really fast. High intensity is by being on a freeway with 1,000 other cars, all going much slower, but there's many, many more of them. Okay. So to do this, we have 3 different thrusts of exploration. One is the energy frontier, again, going to the highest energy accelerators. One is the intensity frontier. Instead of the jet plane, a whole bunch of cars all moving. And the other is the cosmic frontier. That is just taking advantage of making observations about our universe and things that may perchance just fall out of the sky into our detectors. The place where we do the highest energy work is near Geneva, Switzerland. You can see back here, there's the jet, there's the water jet. Geneva's back here. Here's the Geneva airport. And this shows where the accelerator is underground. Many people here at Michigan work on this one detector, which is located underground here. And you may notice there's a couple of people standing on the detector here for scale of how big this detector is. It's a little bit ironic that to study the smallest things, we need things that are really big. So this is sort of the scale of, say, the height of this building that we're in now. Okay. There's another accelerator near Chicago, about 35 miles west of downtown Chicago, which is the US Accelerator, and this is Fermilab. And this accelerator has, there's several parts to it: a linear accelerator, a little circular accelerator, another circular accelerator here. At one time, this was the highest energy accelerator in the world, but when CERN started operation with the LHC, the energy frontier moved to CERN, and now there is a program at Fermilab to capture the intensity frontier. And that will involve building some new accelerators. Yes?
Why does the speed of particles that collide produce different particles? It's like at CERN, they try to get things up to the speed of light.
Yes.
But if they were 10% below the speed of light and these particles crashed at that speed, what's the difference? Or if you look at those 2 scenarios, why does one scenario produce different particles than the other? I never understood that.
So that's a great question, and let me take it aside. What we are using is when we take these 2 particles at very high energy, and at CERN we collide them together. At JPARC we actually just take a bar of gold and smash the particles into it that way. when we give a lot of energy to these particles, and in CERN we're accelerating protons, we give 7,000 times the amount of energy that is contained in E equals mc squared of the proton. So now the energy density that we have when we collide these two particles together is very much larger than E equals mc squared. And consequently, we can take that energy and convert it into masses of new particles. Okay. Now the fundamental theory underlying this says if you just have pure energy, you can create all kinds of particles, even ones that don't normally exist, don't otherwise exist. For example, one of the goals at CERN was to discover the Higgs particle, which they were successful in doing. So it's by giving these particles lots of energy and using E equals mc squared, we can convert that energy into masses of new particles. Does that help?
So you're actually creating new particles from energy?
Yes,
So
we really are.
then the more new particles, basically.
And the higher the energy, the more new particles. And sometimes you want to go to very massive new particles, like at the LHC, and sometimes you just want lots of the boring old particles, like at JPARC. Okay? Okay? Does that help? Are there other questions? Okay. So I first of all just want to locate where JPARC is for you. So you're all familiar with this. Tokyo is down here. Here is Scuba. This is Mount Scuba right here. And JPARC is right up here, south of Hitachi, north of Mito. So this is where we are located. It is a part of Japan that is completely devoid of tourists. No one would ever visit there. No one would ever have a reason to visit there, which is one of the things that makes it really nice. And this is then the JPARC site. Here, of course, is the Pacific Ocean, and here's the set of accelerators. A linear accelerator that starts the particles off and then puts them into what's called a rapid cycling synchrotron. Rapid is correct. This synchrotron cycles 25 times per second. We put a new batch of protons in, they accelerate it up to their full speed, and then we do that over and over again, 25 times per second. The one at Fermilab, to compare, does it once every 8 seconds. So there's factors of hundreds faster here. Now, one of the things that goes on at JPARC is a multi-purpose laboratory, is to take the protons out of this rapid cycling synchrotron and put them into a target inside this building here, which is called the Materials and Life Sciences building. And the purpose for this is to create a secondary bunch of particles called neutrons, which are then used to analyze the structure of materials or DNA or proteins. For what I'm interested in, they take the protons out of here and put them into this accelerator, which takes it up to 30 times the energy of the rest mass of the proton, and then takes them out and puts them into this building down here, which is called Hadron Hall, because this is where we study hadrons. Okay. Any questions on this? So these are the 3 sites, yes?
What difference does it make if you do 1 every 8 seconds or 25 a second?
So the intensity is much higher. So what would take 1 year at JPARC would take 320 years at Fermilab.
Well, I mean, it's just a matter of how many iterations you can do.
Yes,
It
yeah.
doesn't really affect the outcome. Like
It doesn't affect, right,
if
yeah,
you do 25 a second or
yeah.
every 8 seconds, you don't get a different result. You just get more.
You just get it faster,
Oh,
yeah,
oh, I see.
yeah.
Oh.
You get it within a lifetime of a graduate student, yes. Okay. Which can be important. Okay. Okay, a good question. Okay. So now, there's 3 of these accelerators in the world. One that is made by the whole of Europe, plus many other countries around the world. One that's made by the US, and one that's in Japan. And other countries don't have one. China has a very small one. India doesn't have one. How did this come about? Why did Japan invest in this? And so what I'm going to do is tell you just some of the history of the developments in Japan that led up to this. And the first set of developments actually were a group of people who were working on a theoretical understanding of particle physics rather than experiments. The first one is Yukawa, who won the Nobel Prize in 1949, and this is his citation. Atomic nuclei have inside them protons and neutrons, and we all know that the protons repel each other. But somehow within a nucleus, they are sticking together. And people puzzled over how this was possible, knowing that protons repel each other, but they are sticking together inside the nucleus. And Yukawa is the one who came up with the theory that described this. Other really smart people were puzzling over this for 20 years. Enrico Fermi couldn't figure it out. Einstein couldn't figure it out. Yukawa figured it out. And he came up with, his proposal was there should be a new particle, never before observed, that acts to hold the nuclei together. So he made a prediction. There should be this meson. And his theory, so the atom's about 10 to the minus 10 meters. The nucleus is very small inside that, 10,000 times smaller. His theory was the Coulomb force, which we knew about from already the 18th century. There's a new force that has a mass in it, and by this exponential becomes very short range. Okay. So I remember when I was an undergraduate, all physics majors solve the Yukawa potential problem. It's just one of the things that we do as we go along. I remember when I was an undergraduate, and the first time I saw the Yukawa potential and wrote down the equations and saw how it was holding the nucleus together, I felt like I had just been let in on a big secret. That before, none of the physics courses I had before even touched on this problem. And here's the beautiful solution to it. It was for me, it was truly remarkable what Yukawa did. This is a picture of Yukawa at Berkeley. In September 1948, he was invited to Princeton. He went to, this is at Princeton. From Berkeley, Enrico Fermi is here. This is Wick, and this is Segre. This is Yukawa here. This was the year before he won the Nobel Prize. So he was already moving in these circles, and all very well renowned. Here is another picture of him at Princeton. This is him with Albert Einstein. this was really fun for me to go and find all of these pictures of people that I've been hearing about my whole life. Here's another picture of Yukawa with Oppenheimer, a name you may be familiar with, and Tamanaga, who we'll talk about in just a little bit. So this picture was taken just after Yukawa learned that he had won the Nobel Prize. And then this again is at Princeton. So this guy here is Tamanaga, who won the Nobel Prize in 1965. And again, for this progress in theory. One of the, so the theory of electricity and magnetism had been around for a while, and the theory of electricity and magnetism already from the beginning contained the theory of special relativity, but it didn't contain quantum mechanics. Putting together the theories of quantum mechanics, electricity and magnetism, and relativity all together, it was the progress that Tamanaga made. However, when people first started to do this, every calculation that they made resulted in the same answer. Its mass is infinity, its cross-section is infinity. Everything, all the calculations just blew up. You got infinity every place. He came up with this way of saying, well, we know that not everything is infinity. So let's take the calculation and subtract infinity from the calculation until we get just the right answer. And this works amazingly well. The single most precise calculations ever done involve these subtractions of infinity from infinity to get the right answer. And it's good to, remarkably good to 1 part in 10 to the 11. So Tamanaga is the one who really developed this, along with Schringer in the US. Here's another picture taken a year after Yukawa won the Nobel Prize. He was at Osaka. They had a meeting in Kyoto, and here now is Yukawa. Here is Tamanaga, who's going to win the prize 15 years later. And over here is Yoshiro Nambu, who I knew at the University of Chicago. And he won the Nobel Prize in 2008. I mean, I just can't imagine what it must be like to have been in this room. It's like, okay, all you other guys hanging around here, I won the Nobel Prize, you can win the Nobel Prize too. Okay, just, the level of expectations here must have been incredible. Nambu was at the University of Chicago, came from Kyoto before that, and he again made a deep theoretical contribution to understanding particle physics. I want to tell a story. Nambu was such a gentle soul. He was, just very soft-spoken, very kind. And someone in Chicago told him that if you ever get pulled over by the police, you have to bribe them. So he was driving on the freeway and he got pulled over, and he knew, okay, I've been pulled over by the police, I have to bribe them. So he took a $20 bill and he folded it up and put it behind his driver's license and handed the police his driver's license with a $20 bill folded behind it. And the policeman goes, sir, I think this is yours. And just handed it back to him. Yeah, very, very, very kind person. So, and the other two people who won the Nobel Prize in 2008 were Kobayashi and Masukawa. And they have their names, every particle physicist knows these names so well. They came up with a theory that when only 3 kinds of quarks were known, they said we can solve one of the other problems of how did the universe make matter by saying instead of 3 quarks, let's go to 6 quarks. Of course, no one thought, well, there's no experimental evidence for that. So they extended the model from 3 quarks to 6 quarks because doing so meant that they could explain some other phenomena previously not quite understood. They just came up with, sorry for the math, a matrix which converts the flavor eigenstates, quarks in specific flavors, into weak eigenstates. That is, and in doing so explains how the weak interaction works. So this particular matrix, there's several different ways of writing down this 3x3 matrix. This is another way of writing it down. And this matrix comes with 14 equations that say the properties of this matrix must be satisfied. There's 14 equations and 18 parameters in the matrix. And using these 14, this is one of these 14 equations, basically it says one term plus another term plus another term equals 0. That is, if I start here, and if I go, oh, sorry.
It's okay.
If I go along this axis with one of them, and then this along another one, and then this along another one, I have to end up where I've started off. And for experimentalists, it says, measure this side, measure this side, measure this side, measure this angle, measure this angle, measure this angle. And if they don't make a triangle, then there's something missing from your theory. And so there's been huge efforts in high energy physics to measuring triangles. And our experiment is actually just trying to measure the height of this triangle. Okay, so that's the background in the contributions in theoretical physics from Japan physicists as measured by their receiving the Nobel Prize. Okay, so now I want to turn towards the measuring side, the experimental side. So this is the laboratory KEK, and it's near Scuba, and you can see the twin peaks of Mount Scuba in the background. Again, a linear accelerator followed by a circular accelerator. This was established in 1971, and the first experiments took place 6 years later. 10 years after that, it was converted into electron-positron collisions, and in 1994 was converted to making a dedicated machine for studying the B quark, and is continuing that. In 1998, they created a beam of neutrinos to go to the Kamiokande detector, which I'll explain in the next slides. And in 2005, the Tokai campus, where JPARC is situated, was opened. And just 3 years ago, they started the Super KEKB factory. So there's been a long history of high energy physics at that Scuba site in Japan. There's also this effort started, as I just mentioned, started in 1982 to build a very large detector to look for protons to spontaneously decay. And this is the Kamioka. Kamioka is a mine. And this is an experiment that is deep inside a mine to shield it from cosmic rays. And that started in 1982 and operated until 1985. It was then upgraded with more sensitive electronics to be able to detect neutrinos. And that started taking data in 1987. And almost very quickly after they turned on, they made this incredible discovery of neutrinos from a supernova that exploded in the Magellanic Cloud. And those neutrinos from the supernova were also observed in the Irvine, Michigan Brookhaven experiment, which people here participated in, which was located in the Fairport salt mine. You really have to be dedicated to build an experiment in a salt mine. It's a really nasty environment. The KEK to Kamioka, K2K, use the accelerator neutrinos to measure the properties of neutrinos as they go across. And Super Kamiokande was started in 1996, upgrading from 3,000 tons to 50,000 tons of water, and from 1,000 phototubes to 11,000 phototubes. So let's look at where this is. This is where KEK is. This is where JPARC is. This was the K2K experiment from here, and T to K experiment is here. Kamioka is this kind of detector, and we saw pictures of JPARC previously. So this is the Super K detector. It is 41 meters high and 39 meters across. That is roughly the building that we're in would fit inside this detector. It's a very large detector. It is located 1 kilometer underground, underneath a mountain, with access tunnels coming in from the side to be able to get to this detector. And here's a picture of the detector as the water is starting to flow into the detector and fill it. And here you see two guys in a inflatable raft as they're going around inside the detector as the water is going up to service the detector. This was, again, this started off as a way of looking for proton decay and then turned into a way for looking for neutrinos. And for the work on neutrinos, Koshiba won the Nobel Prize in 2002 by detecting both this detection of the neutrinos from the supernova and neutrinos from the sun. Okay. Just in case you don't know, winning a Nobel Prize is a big deal. Okay. But it's even a bigger deal in Japan than it is here. And this was absolutely deserved. And then again in 2015, Kajita won the Nobel Prize for the next phase of research with this detector, which was seeing that not only could you detect neutrinos, but the neutrinos were changing from one kind of neutrino to another kind of neutrino in the process of getting to the detector. And they did this in two ways. One is by looking at cosmic rays generating neutrinos at the top of the atmosphere, coming down into the detector, versus what happens on the other side of the Earth, making neutrinos, and the neutrinos going all the way through the Earth, and seeing that there was a difference between those, because as the neutrinos pass through these very different distances, they do different things. A truly remarkable result. Okay. So this long and distinguished history of both theoretical and experimental work in Japan is what has led the country of Japan to continue to support to do this kind of research. And it's why this laboratory in Japan exists. I'm going to go back and tell another story. After Kobayashi and Maskawa won the Nobel Prize, the following spring I was at this laboratory, KEK, and we got a notification that the laboratory was going to have a very important visitor. And during this very important visitor coming to the laboratory, we were not to go outside. Wherever we were working, we had to stay put for the visitor to show up, for the visitor to be at the laboratory, and then after the visitor left, we could go back out. This, of course, was the emperor coming to visit the laboratory to meet with Kobayashi and Maskawa at this laboratory. The laboratory has, as all laboratories does, has budget problems, and the administration of the laboratory has to decide how to allocate the budget. And one of the things that I had noticed over the previous few years to this was that the maintenance of the grounds had sort of stopped. Bushes were overgrowing. Places that normally would have been mowed weren't being mowed anymore. Just a way of trying to contain the budget. After this visit, there was a very clear path through the laboratory where everything was mowed and all the bushes were trimmed. So I do know where the emperor visited, even though we weren't allowed to know at that time. In a similar way, to the Queen of England, the whole world smells like new paint. Okay, so let's come back to this. Here's what I'm working on, which is this one particular particle, a kaon, decaying in this way to a pion and two neutrinos. The kaon is neutral, so when a kaon is generated, we have no record of that happening. Okay, it's a neutral particle. We don't see it at all. The neutrinos, they also don't interact. We have no record of that happening. Pion also is neutral, and so this within the high energy physics community is sometimes called the nothing to nothing experiment that you want to measure very precisely. It occurs in the standard model only through a very rare process. And by having the standard model process be very rare, it allows other potential processes to reveal themselves so that we can see what else is going on. This is the list of the 6 different quarks. Again, when Kobayashi and Maskawa came up with their theory, they just had these 3 quarks. And they said maybe there's 3 more. They weren't known at the time. The kaons, there's 4 different kinds, making these particular combinations of the up and strange or down and strange quarks. How do we use these particles to answer the big questions that we have? Let's see. So the S-type quark that we start with, within the standard model, there is no way for the S-type quark to directly change into a D-type quark. Okay. The S-type quark can change into a U or a C or a T, but not a D. But the pi 0 has a D in it. So how do we get from an S quark to a D quark? We have to go through this loop of making a U and a C and a T, and then making another interaction where we take that U and our C and a T and make a D. And we have to spit off another particle. So usually in processes you have one of these things, and that makes a process rare. So now we have rare, rare squared, rare cubed, rare to the fourth. This is really not very common. The expected branching ratio from that process I just showed is 2.8 times 10 to the minus 11. This is a small number, okay? And the way we have to do this experiment is we make a kaon. One kaon. Did it decay this way? No. Okay. Make another kaon. Did it decay this way? No. Okay. Do that for 10 to the 12th kaons. It's a lot of kaons. If you are doing 1,000,000 kaons per second, it takes years before we can get to this level of precision. Also, these kaons don't hang around for very long. Their average lifetime is 5.1 times 10 to the minus 8 seconds. That is, if it's going at the speed of light, it might make it across this room before it decayed. They're not around for very long. Now, in the perverse worldview of high energy physics, particles with this short of lifetime are called stable particles, okay? Because the unstable ones are 10 to the minus 23 seconds, way shorter. This one's stable. We can actually observe them. And again, there's only 3 places in the world that can make these: CERN, Fermilab, and JPARC. CERN has decided to do an experiment with K pluses instead of K zeros. Fermilab has decided they're not going to do kaons at all for now, and JPARC is then where we will end up. Okay, so what does this experiment look like? Is we have the protons coming out of the accelerator, and they hit a bar of gold. Okay? Then from that bar of gold, all of these other particles come out: photons, neutrons, kaons, and also a lot of charged particles. We put in a magnet, and that makes all the charged particles go away. And so this is a picture of our beamline. So if you actually stood here and could look straight down, you would see through a series of small holes this gold target where the particles are coming from. This is a picture of the detector. It's in vacuum, and of course, to make a vessel this large that doesn't collapse when you put a vacuum inside is a challenge. And so when the experiment was first being constructed, the question was, where can we go to find a company that's really good at making long cylinder type things that don't get crushed when they have a lot of pressure on them? And the US probably wouldn't be able to do this, but in Japan they went to the Russian submarine factory and said, can you make us something that's not quite a submarine but has many of the same properties than that? It's made of steel and doesn't get crushed when it has a lot of pressure. And so this is a schematic of this detector. The kaons come in here, and most of the kaons coming in, say 97% of them, just will keep on going right out the other end. We won't get to use them. About 3% will decay somewhere in this region, and then we want to look at how they decayed and see, did it make a pi zero, which gives us 2 particles we can detect here. Now, if you remember, there was a long list of other kinds of processes that decay. Remember, for every one of the one that we're looking for, we have 1,000,000 times 1,000,000 of the ones that we don't want to have. And so we have to have lots of detector components to say, oh yeah, it decayed in the boring way. We're not interested in that. So all of these other detectors all around are just meant to say, this was not the decay you're looking for. Okay. So the kaon comes in, decays to a pi zero. Pi zero really is short-lived. It only lives 10 to the minus 16 seconds. And it decays into 2 photons, which are detected here. These are all of the other ways a kaon can decay that we're not interested in. Okay, so we have to get rid of these other 100 billion nuisance decays. Okay, here at University of Michigan, we built the electronics to get all of the data from this experiment and read it out and process it. That is, we want to be able to look at roughly 1,000,000 of these decays per second, which means you got to look at one and then you got to turn around right away and look at another one. It's my graduate student, Stephanie. This is the waterfall of cables coming from the detector. She's working on making sure that they're all connected properly. And this is Stephanie standing inside the detector. Not when it was under vacuum, but when it was still being assembled, just to give you an idea of how big it is. Okay. So now I want to talk a little bit about analyzing the data that we get from this experiment. In physics, it's easy to get fooled into getting the answer that you want to get out of an experiment. So we analyze the data in such a way that we don't know what the answer is until the very last step. And this is what's called a blind analysis. So we write our reconstruction package to put everything together, make an estimate of what all the backgrounds are, and how many kaons we have to figure out how sensitive we are. And we have to also know how many kaons we have by measuring other known decay modes. This is a history of us collecting data at JPARC. So the years start down here, 2012 through 2018, and the blue bars are the periods of time when we were actually collecting data. You see, most of the time we don't have these blue bars. We run typically for a couple of months per year. We would like to say run 6 months per year. The limitation on how much you can run is budgetary. It's just how much money do they have to pay the electric bill for this. So we had our very first run, 100 hours, in 2013. After that, the facility was stopped for a while. We collected more data in 2015, and then 16, 17, 18 collected this amount of data and have collected a little bit since then. So we have 3 different sets of data where we've analyzed it, the 13, 15, and 18 data sets. So this was the first result from 2013. And what's being plotted here is where did the kaon decay? How far out in front of the detector did the kaon decay? And what's plotted here is how much energy the pi zero has going sideways. And here's where we expect to see a signal. In 2013, when we looked at the box, there was one event. Okay, and it was a factor of 1,000 higher than what we had hoped for. So what this told us, and unfortunately what it told the funding agencies, is you have a background you don't have a control over. So we had to do a lot of work as a result of this to figure out what was going on with this one event. So we redid some of the experiment to do this, and also said, this last one took 7 years. It's going to take us 7,000 years if we keep at this rate. So we gotta find a better way to do this. So there were improvements made to the detector, both to decrease the background and to increase the beam intensity. The maximum intensity that the beam can have is a negotiation between the laboratory and the city of Tokai. That is, the council says, we will give you authorization to make a beam of this intensity, and then you have to show that you can operate safely there, and then we will give you permission to operate at a higher intensity. So to increase the beam intensity was both a technical challenge and a political challenge to do this. The laboratory certainly wants to have good, positive relationships with the town. One of the other things that the laboratory and the town have agreed on is that if any construction goes on in the laboratory where you have to cut down a tree, you have to plant another tree, okay? And so one of the things I quickly learned is one way to figure out what the laboratory's planning to do is to see how many trees they're planting. Oh, okay, they're getting ready to do a construction because they're planting trees now. Okay. So from the 2015 data, we increased our sensitivity by about a factor of 10, and we saw no events. So we were really happy about this because it showed that we had achieved the two goals of increasing the intensity and getting rid of our backgrounds. So now we go to the most recent data, which includes this new inner barrel, which you saw my graduate student Stephanie standing in. And this time we estimated we're going to have 0.05 background events. And we looked in the box and there's 4. So, oh no. Okay, so now we have some more work to do again. And since doing this, we have pretty well convinced ourselves that 2 of these events are background, but we do not know what the other 2 are. Okay, so my conclusions. The high-energy physics community in Japan has a rich history starting from the 1940s, and it's one of the few places in the world that you can actually go now to do these kinds of experiments. For me, the past 13 years of working on this have been very rewarding, and the results are starting to become available. We don't yet know what the other 2 events are. And finally, I want to show off my group of very talented people who are working with me. Josh is now working for a company. He graduated last spring. Melissa is still a graduate student, expects to graduate in a year. Monica is a research scientist working here. Molly is now a graduate student at MIT, second-year graduate student at MIT. Jacqueline's a second-year graduate student at Berkeley. Stephanie, who was standing inside the inner barrel, has just graduated. Khalil is in the applied physics graduate program here. Kristen is just starting graduate school at the University of Chicago. Noah won a Marshall Fellowship, so he's going off to England for a year, and then will go to Harvard when he comes back to that for graduate school. Ramon is at UCLA in graduate school, and Brian is in the back row here. Okay, so thank you for your attention. I'll be glad to take questions. Yes.
What is it about the atmosphere or availability of resources that produced so many people in Japan to do this work? I mean, it's a small country, so who put the investment in to get all these mathematicians and physicists?
I don't know the answer to that. Okay, so there are lots of things about Japan that are a little bit of a mystery to me. But I think that's a very good question. I mean, they do take learning and not only science in this field, but science, all fields of science, they take it very seriously. Tsukuba, the town of Tsukuba where KEK is called Science City, and there's many different research institutes in that particular area.
It's a government. It's like a Japanese DOE.
Yes, yeah.
What is the ISTO? National Institute of Advanced Science and Technology.
Yes.
Whatever.
Yes.
Yeah.
And so,
they are funded by the government.
yes. And the government does put a lot of funding into this. The Ministry of Science and Technology does this. I don't have a good answer to your question, but I do agree with you about your observation. Okay. Yes.
Thank you for the talk. So I don't have any knowledge about high energy physics, so maybe my question is kind of silly, but I'm wondering, when you make, two particles collide, like how you sort of do targeting? Because I wonder, so the particles are super small, if my understanding is correct, and if you try to, shot a particle by another, like how you can make sure that those two collide with each other, and so is it like, one shot, one kill level preciseness, or do you have to shoot many particles in order to?
You could be a particle physicist. You got the right idea. So at CERN, where they are colliding protons on protons, yes, protons are very small. How do you make them hit each other? And at KEK now, where they are colliding electrons on positrons, those are also very small. How do you make them exactly hit each other? And the answer is, most times they don't. Okay. So what you need to do is you need to make a lot of particles. Was it 10 to the 13th per pulse?
10 to the 14th.
10 to the 14th. So you take 10 to the 14th per pulse here, and you take 10 to the 14th here, and you shoot these 10 to the 14th particles, and 10 to the 14th minus 1 pass through each other. Okay. And one particle then makes an interaction. Sometimes you don't get any interactions. Sometimes you might get 10 interactions. But you do have to do a lot of very careful manipulation to get the beams to be very small. The size of the beams is thinner than the diameter of a hair. And they have to be controlled at that accuracy over this 27 kilometers going around. Okay. The actual magnets that are used in the final focus to actually make these beams were actually developed at Fermilab and then sent to CERN to be installed there. Okay. But this is a very good question. And the accelerator physicists who have really difficult jobs have all this figured out. So we're happy just that they give us the beams and we get to do experiments. But that's a really good question. Did I answer it okay?
Yeah.
Okay.
And there are associated problems with being more and more successful at making these beams collide at CERN. I work on that with the experiment at CERN. And as one increased the intensity, which was a very positive thing, I'll just speak loudly.
Well, they're trying
That's a
to,
very positive
yeah.
thing. We're up to getting 200 collisions
yeah.
per crossing now, and that's a problem too, because in your detector you get the results of all 200 at
Yes.
one time.
Yeah.
So success can have its disadvantages.
Yes. Yeah. Any other questions? Yes.
You mentioned that there are three places to make kaon: Chicago, Geneva, and Tokai
Yes.
in Japan. And are there any specific, or I should say standard specification for the detector in each country? And also, do you see any difference in result based on the spec of the detector?
Okay, so that's a really good question. So all of these detectors are custom designed, and they are all pushing technology to the limit, or even having to invent new technologies because the current technology doesn't exist. There are some standard practices, like materials to measure energy through the light that it gives off when it's a material. Those are very standard. A tracking detector that follows a single charged particle as it goes along. Those are fairly standard. But the each experiment has so many constraints. Often one of the constraints is you want a detector that has zero mass and is infinitely strong. Okay, that's like, well, there's trade-offs that we have to do there. So there is actually a community as well of basically people who are experts in building detectors. They have their own community, their own conferences, and they trade ideas back and forth. Does that answer your question? Yeah. Okay. So yeah, these detectors, like the Atlas detector, how did 3,000 people come together to make that detector and all the pieces fit? It's just pretty amazing. Okay.
Thank you.
Okay. Any other questions? Yes.
Yes. How many people are involved in an experiment? How many teams, and how do you coordinate all this work? It doesn't look like a very trivial problem at all.
Okay, that is a great question. Okay, so I didn't show the institutional list, but there's on the order of 10 different universities and institutions to do this, and sometimes, when people are working together, there are conflicts that arise. The major advantage that we have is we are all driven to the same goal. Okay, we all want to make this experiment work. We're all doing our part on that. We're all making our contributions to making this experiment work. You're right, we don't really have a boss. Okay, we each are bringing our own skills and talents to the problem. Different people have different skills, and they bring that. So there is not a very good, strong organization. It is just people coming together because they want to all accomplish the same thing. Okay. I don't know, Jay, do you want to comment about Atlas? Because it's much bigger.
Atlas was studied by an Australian institution, business school, as to how we could bring 3,000 people from with 24 languages and 40 countries and put together a detector and have a administrative organization. I think they were totally amazed that it worked, given it is quite loose if you look at centralized organizations of 3,000. It's amazing. And my personal experience was trying to coordinate the development of electronics between the Dutch, the Germans, the Italians, the Americans, and committee meetings were always very interesting as to how people participated. I always thought the Italians and the Germans liked to argue for the sake of arguing. But sometimes they were talking about 6 and a half a dozen, but we got there. Issues like, are there benchmarks for when we reach this level of development? And the Germans and the Italians disagreed on exactly what constitutes a benchmark in design. But it was fun. I consider that last 20 years of my career working on Atlas as probably the most exciting part, and part of it was the international aspects of it that gave me an opportunity to try to run such an organization, which was a challenge.
So we have, our whole collaboration has a meeting every week. It is at 9 a.m. in Japan, and now 8 p.m. on Thursday, 9 a.m. on Fridays in Japan, 8 p.m. Thursdays here. And I've often complained, Brian will know this, if the meeting goes really long, like after 2.5 hours, my Japanese colleagues tend to just say, well, it's already 11:30, we'll just keep meeting until lunchtime. For us, it's getting really late. But there's lots of challenges because this is the science we want to do. It's what motivates us. You had a question?
Thank you, Myron, for the fantastic talk. I feel like I learned a lot. I still don't know if I can explain how K-on works, but it was great. I can't ask any intelligent questions about physics, so my questions are social, political, cultural dimensions of all this. Couple questions. First, so I don't think it's any surprise that any modern nations today invest in science and education, and over time science develops. And in Japan, by the 70s or 80s, it produced Nobel Prize winners. I think China's going through the same process, Korea, maybe India to a certain extent. And in that process, I'm curious about this, how scientific breakthroughs take place. And Yukawa and Tomonaga and all these people, when they came up with those ideas, was it a matter of just having a fresh set of eyes to this, to an old conundrum? Or is there something about them coming from Japan, something about the Japanese ways of looking at things? There's a lot of a romanticized argument like that in Japan, especially because they come from Kyoto University, where I'm from, and they all talk about how they walk around the paths of philosophy, and then they came up with all these ideas are there, but I'm not sure to what extent it's true. So I'm wondering if you can comment on that process of scientific discovery, and is it, it's science, so I don't know how cultural processes matter, but I wonder if you can comment on whether them coming from Japan, not Western nations, have anything to do with it.
So certainly while the language is quite different, the mathematics is more universal. And they're working deeply in the area of mathematics. I think there is a cultural component to it. Tomonaga, in dealing with these infinities, everyone else looked at this and go, oh, well, that's never going to work. I give up. Fermi, who wrote the book on nuclear physics, didn't come up with this idea of the meson, although once Yukawa presented it to him, he immediately got it and knew what to do next. So I think there is a strong component of don't give up, just keep working on it. Keep working on solving these problems. What I found amazing in doing this studies was just the locality of all of these people working together was centered on Osaka and Kyoto. It wasn't spread throughout the country. There was something about these people working together, and also the trips that they made to Princeton and to Berkeley to get fresh ideas. That picture of the 3 Nobel laureates all sitting together in one room, it just says a lot for what their daily conversations must have been like, and what the expectations were like, and what the ideas that were coming out of those conversations were like. I don't know if there is something specific with Japanese culture or not. I would have to know a whole lot more about Japanese culture than I do.
That's what we used to have over University of Tokyo. Is that first several winners of Nobel Peace Prize are all from Kyoto University. Anyway, the second question. So budget issues, you touched on it a little bit, and this is probably a little less intense today than, I don't know, 6-7 years ago. The Democratic Party of Japan had sort of intense campaign of cutting down budget everywhere, including those kinds of scientific budgets. And I think there was more attention to supercomputers and accelerators, but there was some pressure. And there's the concerns about safety, right? Nuclear physics faces a lot of that. And I'm wondering what kind of messaging these people may be doing to appeal to the public, the government officials, about the utility of all that, and aside from Nobel Prizes, how do they try to convince the public about the benefits of these?
So, in the time that I've spent at Tokai, I have seen a huge shift in the concern about safety. In fact, there was a conference, there was a workshop at JPARC just about the safety culture at JPARC, and I made a presentation there telling about my experience with the safety culture at Fermilab. Because there is an unfortunate history of people not paying enough attention to safety. Now, I personally insist everyone in my group operate safely. So one of the things that I do is I do not let any of my students or postdocs drive in Japan. Okay, because that's one of the most dangerous things that they could do. We all have bicycles, and if I'm going to see you riding a bicycle, you better have your helmet on, or I'm going to give you a lot of. And helmets are not so popular in Japan as they are here. But the safety culture at JPARC underwent a huge transition while I was there. You probably, many of you may remember there was, in the late 1990s, a very serious accident at the Tokai nuclear material reprocessing plant. Do you know what I'm talking about? Yeah. Okay. And this accident was, from my study of it, there is an intense pressure to keep schedule, to do things on time. And sometimes that pressure to keep schedule results in people taking shortcuts to try to, if you get a little bit behind, try to catch up. And the nuclear fuel reprocessing accident was they would do small batches of reprocessing, and they were getting behind. They thought, oh, we can just do a bigger batch. Well, if you take a whole bunch of uranium and you make it too big, it goes critical, which is exactly what happened in that case. I showed you the picture of, we took some data in 2013, then there was a long gap. That was because of an accident, okay? And the accident was a magnet inside the accelerator malfunctioned. And instead of the beam going around and around and around for over 2 seconds, a little bit coming out into the gold target at a time, when that magnet malfunctioned, all of the beam came out into the gold target at once. And it vaporized the gold target. Okay. Now the gold target had been used, it had a lot of radioactive nuclides within that gold target. The gold vapor that came out of that was not completely contained within the target itself, but came out into the building. Okay? And so far, everything was working as it should. The radiation monitors in the building said there is a leakage of radiation. They shut off the accelerator. But then one of the operators made a decision. Is this alarm of radiation detectors real? Or is there really radiation, or have the alarms malfunctioned? I know. I'll turn on the ventilation fans. And if the ventilation fans if there's really radiation, the ventilation fans will take it out. Bad idea. Because right next to JPARC is a nuclear power plant. So 15 minutes later, they called up and they said, our radiation monitors have just gone off. And we've looked around our plant. We don't have a leak. Do you? And the town was very upset by this action. So there's a very strong message about safety that came in after that. I think from the top all the way down is we are going to operate safely and take the focus off of operating on time. Before the radiation accident, you could go online to the JPARC website and you could see their schedule for 2 years in advance. 5 o'clock, 6 months from now, 5 p.m., they're going to do this and they're going to do this. And there was an intense pressure to maintain that schedule. Those schedules are no longer even published. We do things when we are ready to do them. So safety has become a much bigger concern. It took an unfortunate accident. No one was hurt in that accident, but it really raised awareness. My student was there at the time of the accident, and all of the people that were there at the time of the accident had to have whole body scans done to make sure that they did not have any radioactive material inhaled or ingested. Everything was fine. But we got from the director of the laboratory a letter of apology that I was to deliver to the University of Michigan president, saying we are sorry that we put your student at risk. So this letter of apology also contained another apology. I apologize for not being able to apologize in person. So, but yeah, so I think the safety culture, just on this topic, I was at Fermilab when Admiral Watkins was the director of the Department of Energy. And how many of you know about the book that was assigned reading for this summer's class, Whole Body Burden, about the Rocky Flats? He was the one who had to go in and clean up Rocky Flats. And all of the national labs, including Fermilab, we were shut down. We were shut down for months and were told, until you guys get your safety organization right, you're not going to be allowed to do your science. And that was the story that I took to JPARC. So that's a long-winded answer to your question. Does it? Okay.
You already answered my some questions, but partially. But my understanding, science approach is create the theory, then to identify or understanding to the theory is correct. That is like experimental. You have many things. So then I understand also like he mentioned already like the many particles to different particles hit each other. And you would like to be increase successful ratio, and also increasing to beam strengths. That could be also scientists expecting to next level.
Mm-hmm.
So my question is what's kind of but everything is a theory, not kind of prediction. Not we don't know everything yet. So if we increase, two questions. If we increasing to the beams, do you already know some risks? And also, if we increase the successful ratio to hitting two particles, 80%, 90%, 100%, probably creating huge energy. So is it any risks I don't know, earthquakes or a much big impact for the your facility or area or we don't know, we cannot see it, is right?
Yes. So so you mentioned several things. One is from theory to experiment is not nearly as linear as you described. It's sort of a tangled up mess. And you make progress in experiment, you make progress in theory, and they feed back and forth to each other. Another thing that you wanted to talk about was, again, I think touches back on safety. People are very committed to operating these facilities safely, and there's many hazards. I remember the very first time I was at KEK and went to a safety training in order to get my ID card. They showed us a video of all the things that you were not supposed to do. And we looked around the room and we found examples in the room of everything they told us not to do. And it's much better now. The risk from earthquakes in this part of the world is genuine. And I remember standing outside of Hadron Hall and complaining. I said, I can hear the waves crashing on the beach. I can smell the salt water, but I can't see the ocean because there's this big hill in front of me. Well, in the 2011 earthquake, I know why that hill was there. That was the tsunami barrier. And it saved the laboratory from being affected by the tsunami. There was significant earthquake damage, but there was not tsunami damage. And that was due to the forethought of the people who built the laboratory. There was actually a study of a small river near Tokai, and they analyzed the deposition of the sediments over the last probably 1,000 years to say what was the biggest tsunami that's ever been in this region. We're going to protect against that. Okay, so people are genuinely concerned about safety and about operating these facilities safely. Okay.
My question is if the huge all the particles hitting each other,
Yes.
Successfully 100%.
Yeah.
It could be creating huge energy.
Okay. To set the energy scale, it is about 1/1000th the amount of energy contained in a candy bar.
We don't know how big is, right?
Well, we know how we can calculate how big it is. It's
the facility can survive.
yes, yes, yeah. Okay.
All right. Well, thank you very much, Professor Campbell, for the lovely talk, and
Thank you.
thanks everybody for coming.